Welcome to myprojectbazaar.com. Now we can going to discuss about the product high power density single phase 3 level flying capacitor bug power factor correction rectifier. Next we can going to discuss about the abstract of our product. The proposed system we can implement for the specific applications like 3 level flyback capacitor of power factor correction rectifier, and this is one of the active pulsing power buffering, and this is one of the technique for reduce the energy storage system to record the high energy power factor corrections, and this is one of the existing process like for single phase solutions with the active power factor pulsating corrections we can generally suffer as high voltage stresses, and this is leading to the power losses for the high voltage and high rating for the semiconductor switches. In this system we can existingly we can failure for the high voltage stress is a main problem of our existing work. In this paper will be proposed to add on or 3 level flying capacitors for power factor correction rectifier with PBM with for embedded switching pulses will be imported, and this is a different plotters for the clamping circuits we can imported the voltage stress, and we can minimum of the voltage stress in specific switches, and the functionality of entire our diode rectification will be slow, and this is an our real prototype output for that 48 watt power in 48 voltage and 1 amps in current in real time hardware, and this is an high voltage stress for the 72% is a reduction to of the buffering capacitors like, and 23% for the magnetic core size, and this is a new approaching to formulate our single phase power factor correction rectifiers with the active pulsating for buffer we can dynamically boost it on our efficiency, and this is an our buck converter can control the control pulses to our converter. Next we can going to discuss about the flow diagram of the our project. The first we can going to discuss for the our AC grid. The AC grid can fully generating for the purely sinusoidal wave of this AC grid, and this AC grid can passing to the electromotive filter. This filter can magnetize the our capacitors with inductors. We can parallel for that this block, and this block is magnetizing the current, and high voltage stress we can relieve for that this specific block. The specific class is moving to above our current to voltage for diode rectifier, and the diode properties we can forward the we can forward region blocks, and some general our diode breakdown region we can occur that after we can getting the purely DC wave, so we can convert it for generation of AC grid it is converted to the DC. So this diode rectifier can pass it to DC. This is in passing that flying capacitors bug power factor correction rectifier. So this is an one of the three port switch, and these 3 port switch we can control for the flying back integrated with the flyback capacitors. So these flyback capacitors we can integrated to these control pulses. These control pulses we can different types of blocks we can using that, and we are using the repeating sequence, and PLL, and we can absolute functions we can using to control that pulses. We can generating the PWM, so they can generating PWM reference we can taking that our DA and DB of the specific block. So this is an DA and DB specific parameter we can pass into the our 3 different switches for the generation of PWM. So these control pulses can control the flying back capacitor buck power factor correction rectifier. So this is an automatically passed to the our LC filter. The LC filter can reduce the noise we can deliver to the load. So we can using the this load we can using the type of load we can using the R load. We can some more constant input we can getting to the load, nearly we can getting the 48 volt getting that maximum load side of this load, and the current will be getting for nearly 1 point something we can getting that values. Next we can going to discuss about the flow diagram of the product. The proposed system implementation done in MATLAB version 2017b. These corresponding elements are connected from the circuit diagram of the product, and the scopes are connected from the from 2 functions of the our blocks. And next we can see about the our circuit diagram of the our product. This is our entire circuit diagram of the product, and this is an our AC grid, EMI filter, and this is an diode rectifier, and our power factor correction buck converter, and these are flyback capacitors, and these two flyback capacitors, and this is on load, and the corresponding scopes are connected, and this is on our control blocks. Everything is connected from the our base paper of the architecture. And next we can see for the discuss about the our results. These scope blocks are connected from the from two functions. So this we can using the example, we can take the VAC are connected from the voltage across that block. So we can take it this for scope output. This is a voltage of the our AC grid. Nearly we can getting that 150 amplitude range for the our AC grid. And this is an clamped negative wave sequence of the AC voltage. This is an half wave for our AC grid voltage. This is our comparison plot for our AC grid, and a half a AC grid of negative sequence will be cleared. We can using the absolute functions. So this is an halfway will be generated. This is our grid current. This block is when VC, the VC capacitance voltage, we can getting the nearly 48 amplitude range. So this waveform generator is 48 range for the amplitude range for that this voltage capacitance. And this is our VDC nearly we can maximum peak for 48. So we can given to the level of 48 peaks using that OE x-axis zoom pan, and just click at that, and this is a maximum amplitude range of 48. This is on load voltage. This is similar to VDC because of the VDC is across us to the our load. So this is an exactly same as 48. And another thing, this is on our switching pulses is on we can using the three switches, and SA, SB and SC. SB and SC are complementary switches, so we can SB is a complementary form of SC. So it will be off and it will be on. So we can using that these different types of pulse, and SCA is on different types of duty cycle ratios, and different pulse with we can generated. And this is on our DAB block. This is our DA block. This is for not noisy. This is we can given to the saturated input, so we can generate this type of waveforms. And this is unlike stamp inputs. For that we can slightly amplitude will be off on on. Randomly we can generate it. We can using the auto scale, and using x-axis zoom in pan, and just click on x-axis, so we can generating the waveform. And this is our carry. We can carry for DA and carry for DB. So we can nearly 0.8 saturation region will be generated. So this is an inverse to this. This is carry B, and this is our power factor. Nearly we can maintain the one power factor for that our generation of AC grid to contain that nearly 0.9 something we can generated.